So today we're going to learn about the conservation of mechanical energy, and we'll do some practice questions on it. So the title being Conservation of Mechanical Energy. So what does that mean? Well, first of all, we have energy. It's split into mechanical and non-mechanical. We're going to focus on the mechanical side, which is kinetic and potential energy. Non-mechanical would be stuff like heat, sound, light, things like that. There are two types of potential, which is gravity and elastic. We're going to focus on kinetic and gravitational potential energy. We will not touch on elastic today. So, conservation of energy, simply put, is energy cannot be created or destroyed, but it can change from one type to another. So you can transfer the energy, but you cannot create it out of nothing. You cannot destroy it. You could lose energy to the environment through heat and sound, but you will not lose as in destroy energy. So looking at this, the snow person, what's it called? Skier is coming down and across the snow. So what happened while this was happening? Well, at the top, his potential energy was full. And as he came down, he was losing his potential energy, but as he's coming down, look what happens. He is gaining kinetic energy. So this is reducing, this is increasing, but the total stays the same. It is full. This is the total amount. But afterwards, some snow that slows him down. Work is done. He is doing work. So the energy becomes work, and it gets lost into the environment through to friction and sound and all sorts, like I mentioned to you earlier. The key point we need to know is right up until here. If I have the potential energy here, all of that will become kinetic energy down here. If I had 100 joules here of potential energy, this would be 100 joules of kinetic energy. This would be EP, and this would be EK. The potential energy here, of course, would be zero, because I'm on the ground. The kinetic energy, of course, up here would have been zero because he wasn't moving. He was standing, waiting to leave. His starting speed would have been zero. So that makes sense. E total is EK plus EP. That's the idea behind this. Okay? Amazing. So here is another example of a pendulum. It's swinging. As it's reaching the center, it's getting very fast, but as it gets to the top of the motion, it slows down, stops, and then comes back again. And as it's slowing down, it's getting higher, so the potential energy, look, the higher, the potential energy is increasing, I should say. So that was 2 meters. And then it will go back down again, and it's going to reduce the height, reduce the potential energy, but it will increase the kinetic. So it's going backwards and forwards, conservation of energy in play. At the bottom here, look how fast it is. It's 5 meters per second here. It drops to 0 up here, like that. I should say 0 though. And then it keeps going. There it goes, 0. It's a little bit slow. Okay, so putting this into context then. Conservation of energy. Here is a question. Mr. Fessel kicks Alyazia, who has a mass of 50 kilograms, into a 5-meter deep hole. What is the speed of her as she reaches the floor? So for this everyday scenario that can happen, we need to calculate her speed. Well, first things first, we know that she is falling into a height, a deep 5 meters all the way down here. So I can calculate the potential energy to start with. That'll be useful. mgh. 50 times 9.8 times 5. That's 2,450. If her potential energy here was 2,450, her kinetic energy at the end will also be 2,450. We found the kinetic energy using the potential energy, so a half mv squared. A half times 50 times v squared. Shift solve will get you the answer. And you can rearrange the formula as well to get V, which I've shown you in a previous video. Another example of this, you have a ball of 0.6 kilograms dropped from a height of 2. It was dropping from rest. To find the potential energies is mgh. We'll get the potential energy using mgh. 0.6 times, we've used 10 here, but it's not a problem, times 2, which is 12 joules. The kinetic energy would have been 0 because it starts from rest. As the ball hits the ground, the potential energy has dropped because it's going down to 0. All of that potential energy becomes kinetic energy. So KE max, GPE, again, EK, EP, doesn't matter. This is MGH, 6 times 0.6 times 10 times 2, 12 joules. So the potential energy here all became, this was 12 joules, this all became kinetic energy, 12 joules. Potential energy halfway down, well, you can do it, 0.6 times 10 times 1, you get 6 joules. What is the kinetic energy as it reaches the height? Well, I know the total was 12. If 6 of that becomes potential, I can do 12 minus 6. I don't need the speed for this one. I could do 12 minus 6 to get me 6 joules. So, total energy before is the total energy after. Potential kinetic equals potential kinetic. So obviously in the last case, this was 0 to start with, and then the potential became 0. So that was 12, and this was 12. So that's what happened in the previous example. You can do it like this. You could write out the formula like this if you like. Another example here, a student with a mass of 55 kilograms starts from rest and slides down with the friction that is 3 meters high. So there is friction here. Compared to frictionless, the speed will be what? So if I have friction, what will happen compared to without friction? So of course, if there's friction, some energy will be lost to the surroundings through heat. That means if I had friction compared to frictionless, of course, there will be less speed. There will be less energy available. Some of the energy will be lost. So if I'm here going down, that is supposed to be me on a slide apparently, and there's friction here, so some energy is lost into heat. No idea what I'm drawing, but yeah, so comparing to frictionless, it'll be a nice and easy slide all the way down, and I will have more energy. If I started with 100 joules, because of friction, maybe I only have 90 joules here and 10 joules is gone to the surroundings. That could have happened. So, 10, 90, that's 100. Over here, if I had 100 joules, I would continue on with 100 joules, maybe, without any friction. So the idea here, there would be more energy because a half mv squared. This is how you find energy. No idea why I'm writing it backwards, but yes. So that's the thing. Less energy, less speed, of course. Why? I've just explained why, because energy is lost to the environment. Great. So, does it reflect conservation of mechanical energy? Well, not really. It doesn't really help us because friction, energy is lost. But does that mean the law of conservation of energy has been violated? As in, have we broken the law? No, actually, because the mechanical energy did transfer, but it was transferred to a different type, non-mechanical energy, heat energy to be specific. So some quick notes here. Conservation of mechanical energy, potential or kinetic, is only valid when there is no non-mechanical energy involved. So if you mention friction, which means heat, or sound, or light, anything like that, then we cannot use conservation of energy. This will only work if full kinetic energy goes to full potential energy. So energy can be conserved even when the acceleration changes. It can be lost due to friction as heat. These are some key points to keep in mind.